The another part of alkene synthesis. In the previous classes, we have done through pyrolysis. In these classes, we will see the alkene preparation through fragmentation reaction. This is very important topic. So here, today I will go to very advanced level. So I will finish all the example in chapters first, then we will start journal review. So once all these topics are covered, then you will find that whatever the question comes from this fragmentation part, you can easily access that. So first point will come, for which kind of system this fragmentation reaction mainly takes place. So we'll go to the fragmentation part. So which kind of system the fragmentation starts? So it will be, first point will that conformationally locked. Conformationally locked. I will explain why I'm telling conformation locked. Number 2 point is that the 1,3 difunctionalizations, and the point is that the group that breaks and the bond, CC bond, that the group that CC bond breaks and another CC bond breaks. These two has to be in anti-periplanar conditions. Anti-periplanar conditions. If these three things occurs together, then we will find a fragmentation part. So this is the first, the molecule has to be conformationally locked. Number 2, it has to be 1,3 difunctionalizations. Number 3, CX and CC bonds have to be in anti-periplanar conditions or anti-periplanar orientations. So this is the fundamentals for fragmentation reactions. Now this is the general representation. So let's say it's a conformationally locked molecules, and this is the OH group, and let's say this is the X that is going to leave. Okay, sorry for the convenience. So this is the OH group that will break, and if you look at here, this is 1, 2, 3. We find the functionalization at position 1 and at position 3. It's the point to satisfy 1,3 difunctionalization. I told that this molecule is conformationally locked. That's why think about it as a conformationally locked. Now look, these bonds is going to break and this bond is going to break. So these two bonds are in anti-periplanar conditions. So these are the anti-periplanar conditions. CX is CX and carbon-carbon CC bond. In this particular conditions, orientation, the fragmentation rate will take place. How? So it will break, and this is going to break in this fashion, and this is going to leave. As a result, if we draw the same sketch, what we'll get, we are getting one double bond here, and this is the things here we have now C double bond O R group. That is just for representation I did it. Actually, the group looks like these things. There's the 6 carbon are 1, 2, 3, 4, 5, 6. Yeah, this is the things that we're going to get in these conditions. So again, just for remembrance, as we are learning first, then we'll show you the question solving approach. So that's why I'm emphasizing here. Conformationally locked, 1,3 difunctionalizations, and anti-periplanar conditions. CX and CC. That's why this fragmentation reaction takes place. Basically, this fragmentation reaction is called drop fragmentations. This is called drop fragmentation. fragmentations. Now we'll show you the real example for these things. And yeah, let's say this hydrogen is here and this hydrogen is here. And we have one OTS group. OTS basically is a good living group. So this is decoupling system. So decoupling system is conformation locked. This looks like this. So now the point on satisfied decoupling system is conformation locked. This hydrogen is here, this hydrogen is here. Now we have OTS group here because this OTS group and this hydrogen on the same directions. Here you find that this hydrogen and this OTS is on the same directions. That's why it is the orientation, real orientations. And this is the, sorry, it is OH, this is OH, and this is the OH group here. So look, 1, 2, 3. We have 1, 2, 3 difunctionalizations at 1, 2, 3 positions. Now, if we use the base, what will happen? Base will decoder this, and this bond will break, and these two are in anti-periplanar conditions. I have just for understanding, I am making it bold. These one is anti-periplanar. This is going to break. This is going to leave. As a result, what we are going to get? Look, this is the this and this. So we are going to get a transalkene. So alkene will be here, and ketone will be here. E product. And why this is a transalkene? This is a transalkene because the trans is here. This, and this. Now, if the orientation is being changed, so for example, if the decoupling system is quite different, then what will happen? For example, if this is a cis decoupling system, different type of system, this is definitely not decoupling. If the system becomes cis decoupling, then what will going to happen? Let's say this is example number 2. You could see that. So this is now OH, and here we find that these hydrogens is on the opposite side than that of the OTS group. So this is a cis decoupling type of system. So students, please be patient. At the end, you will find that whatever the program I'm showing, I show every details of these things, not a single place to memorize something. You will learn a lot of new things. So these books sometimes might tougher, and today I will cause the whatever the example is given in this book, I will show the double example from the outside this book. So this is cis decoupling system. Now you have to draw these orientations. How we can draw that? So this is one ring, one chair form we have drawn. Now you have to make this hydrogen and OH at trans positions. That's why this hydrogen will come here. This is the hydrogen and this is the OTS group. So I have drawn that part because see, this OTS and this hydrogen is opposite to each other. That is shown here. Now I have the OH group will be here. So I have to draw this these things. As this is hydrogen equatorial, this hydrogen, this carbon bond will be in the axial position. So this is the axial one. Now I am trying to show you how to draw this. Now I will just make a cyclic kind of things here. So this is going to be these things, and here it is. We have drawn another cyclic. So this looks is very bad, but you understand this. So this is the OH here. Now look, these hydrogen and these OTS is opposite to each other. Here we have find some cis orientation in this fashion, cis orientation. Similarly, we are using base, so base will decoder this OH, this bond will break. So this one and this one is anti-periplanar, so this is going to break and OTS is going to leave. Look, the double bond is getting here, that is in anti-periplanar conditions. Actually, the cyclohexane do not fall into chair form, so that's why I'm not showing the double bond in the chair form. That will be totally wrong concept. That's why I'm going to just show exact structure how this look like. So now we understand there will be double bond and there will be carbonyl compounds. So let's see This C double bond is here, and the double bond will be in cis orientation. It will be here. Just if we count the carbon number, you will get to understand. With respect to this carbon, 1, 2, 3, 4. At number 4, it will be cis double bond. So with respect to these carbons, 1, 2, 3, 4. We have these things. Sorry, 1, 2, 3, 4, 5. At 5 position, we have double bond C. 1, 2, 3, 4, 5. So in that way, you can get. So what you understand, if this is a trans-Decaylin system, we are going to get trans double bond. If this is a cis-Decaylin system, we are going to get cis double bond. So that is the tricks after learning. If it is trans-Decaylin system, we are going to get trans-alkene. If it is cis-Decaylin system, we are going to get cis-alkene. So I hope we have got this point, what I'm trying to say. In exam, in order to these things, just see what we'll do in the exam, just find, okay, it's a trans-Decaylin. I want the data now, count. So where is OTS, they have a double bond. Now count the carbon number and put the double bond. So you can solve it in seconds. Then I'll go to some different examples. So it's for the constant system. If the system is not constant, then what will happen? So this is the example. For example, we have been given these systems. We have this 5-member ring, and now here we have a 6-member ring. So this is taken example from Carothers. It has a real journal name, but I'm not saying. I just in Carothers as a reference. So OTS is a living group, and this is methyl group. Here we have orange group, and here we have OH group, and here we have methyl group. Now, if we treat these molecules with sodium hydride, then what will happen? Sodium hydride will abstract this photon first, this one. So it is going to be here O minus. So one, it is O minus. So okay, I'm showing it directly. So let's say this is the OH. This is going to break, and look, this bond and this bond is anti-periplanar. So this is going to break and this is going to leave. As a result, we are going to get, we'll have a double bond here. That is the corner of this 5-member ring. Sorry. So this is the 5-member ring. So here we have the double bond, double bond O. Now this cyclic ring cleaves, it's become linear. How this is going to be linear? This is here, this carbon is here, this is here, here this is the double bond that contains one OMe group and another methyl group. This OMe and this methyl group, because we have one methyl group here. This is the methyl group. So this is done. This part is done. And in these reactions, we have this methyl group. And here double bond group. So it is OH. If after that we treat these molecules by methyl lithium, then what will happen? If we treat these molecules by methyl lithium, see how much interesting. This methyl group, that is methyl lithium, that is in my minus lithium plus, this is going to attack this one. Okay, so then let's say we have used the stereotic solvents, which will be protonation. So it is going to be this one. So here it is now. Okay, I'm going to show what will happen. Let's draw it fast. Every step I will explain. Now I am drawing this sketch, whatever we had. Now let's say this is the double bond. Okay, so this is the part, the top part. Okay, so this is now OH. Look, this is this OH and this methyl group are on the top positions, add on the above or top position, now this methyl will attack from the down positions of this double bond group. If it attacks from the below position, so it is attacking in the below positions as this OH is on the top positions. If it attacks from the below positions, so this OH is going to be on the top positions and that methyl group on the below position. Okay, I think it's clear to you. In the next step, we have used tosyl chloride. Tosyl chloride. So this reaction, they said double fragmentation is single reaction. That's why I'm just putting so much time here. So here we are. This is the alkene part. This is here is the methyl group. So this will be OTS group now on the above sides. And now here this OH is on the down sides. Yeah, it is on the downside. So these two reactions are done together so that this OH become OTS directly. So I shouldn't, basically it is incorrect, but MELI followed by this one. Why it will be minus that, okay. So the thing is in the same time. So it is going to go OH. And now we have this methyl group here. So if I use a base now, the base may be sodium hydride. We are using this. So this is going to extract. So this is going to cleave here. It is going to leave. As a result, we'll have these things. So now if I make it linear, it's C double bond O, this is R, and there should be total 9 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we have one this group and one methyl group, and here we have at 5 positions, we just count it 1, 2, 3, 4, 5. At 5 positions, we will have one double bond. So this is the things that double fragmentation reactions in the same molecules. It is very interesting example. Just go through the book. You will understand. So it is double fragmentations. Okay. Now, so fragmentation also possible by boronate esters. So boronate species also can make fragmentations. Boronate ester, not boronate ester, boronate species, I should say. How it do that? For example, we have these things. This is the methyl group, and this is the leaving group, OMS, the methyl groups, and this is the methyl group. This is the double bond here. It means that it's a constant system. It conforms a lock. So if we use one B2H is a diboron, you know that diboron reacts with the double bond, and not only reacts, it reacts from the less hindered side. Less hindered side. So when we talk about the boron chemistry, I will tell all these things in details. So less hindered side additions. So then what is going to be? So now once the boron adds to this double bond, now it is a cyclohexane ring. That ring can go into the chair form. Now this cannot go into the chair form, but as this double bond is taken up by this B2H6, these two cyclohexane ring can go into the chair form. Now I will draw the chair form. Previously I cannot draw its chair form because the cyclohexane do not fall into the chair form. So what will be the chair form? The clue of chair form, drawing chair form is here. How will you draw that? Let's blindly draw one chair form here. Next, depending on that, I will tell what to draw that. Now look, this is the OMS group here. We see that this OMS group and this methyl group in the same direction. So I have to keep this methyl group here. So is this methyl group here, then this is the equatorial bond that is going to come from the next side 6 number ring. If this is the equatorial, I will put one axial bond here. Now I will draw these things. So this is the chair, it's ready. Now we have these boronate groups here. B, and we know that it can consume another molecule, so that's a here. I think we have got this point. So look at it here. that will help you to draw the chair actually. So this is the constant molecule is ready. So just put the substituent here. It is not that much important. Now, if you use a base here, see now our system is ready. This one now anti-periplanar to these ones. Base will attack there. This bond is going to cleave. This is going to break, and this is going to leave. As a result, so again, so this is fragmented into an alkyl system. I hope you understand this. This is so here we have one double bond and you will another double bond here. So just if you count the number, you will have another see the double bond is here, another double bond is here, and we have two methyl group here. Okay. And do not use the tricks here that I told. If it is trans decoupling, the trans double bond, it is not the decoupling system. That's why it is not applicable here. You look at here, so see this is a trans double bond. Now put the trans here, and here it is double bond is here. So this is also a transit. This transversal. So both are in transversal. So both are double bond in transversals. So whatever I discussed here, routinely questions are asked from these things in GET or NET. This is very much important topic, and people get confused in here. Where should I draw the chair from? Why should I not? And how they are, people get confused. The chair form will be locked and anti or in a single orientation. That thing become clear here. So now here I am to see, I have to show you another interesting example that is not in this book of Carothers, even not in the book of some important books like Clayton or Perry Sandberg. This is totally outside. So because if there's some advanced question comes so that you can address that, that is very easy things. It's Crob's gamma amino fragmentations. That is totally new thing, is not even taught in MSc course. Crob's gamma amino fragmentations. So the name is there, gamma amino fragmentations. So we'll sketch a gamma sequence. This nitrogen here. So let's say this is X, the leaving group. So this carbon is a alpha, this carbon is beta, and this carbon is gamma. So in gamma position, we'll have one amino group. This is the amino group. CH3, CH3. Now it's a gamma amino group. And this X group, this is the fragmented skeleton split. So the borderline are anti-periplanar to each other. Okay, that's the main conditions. In this fashion, what happens? This lone pair goes and this leaves. As a result, what we are getting this thing. N now is double bond plus, and this is going to be this one. Okay, so this will fragmented here, and we'll have these alkenes. Plus, we'll have this alkene group. Another framework, this is a gamma amino framework. Another, this is also one gamma amino framework. See, so this is the X is here. For example, X is here. This is alpha positions. This is beta position. This is gamma position. Here we have one nitrogen atom. This is gamma amino group. So here we have lone pair. This one, and this is anti-periplanar conditions. This is one gamma amino framework. Now I show you a real example of gamma amino framework. So just have a look the first example. Mm, yeah. So if it is given, what will be the product? This is hydrogen. This is the hydrogen. We have OTS group here, and here we have N cis. Now look, if we hit these molecules, then this lone pair is coming here. This is breaking. Not this is breaking. Uh, okay. Mm, okay. This will be not in this direction. This will be opposite directions. In this direction, what will happen? I will show just in next examples. If this look, so the bond that is going to break these bonds, because these bonds and this bond is anti-planar. So after hitting this one, this load will come here. This is going to break, and this is going to leave. As a result, we are going to get the alkene. So how will be the alkene? Let's draw the first framework. So this is the framework. This is nitrogen here. We have double bond here. This is plus. That is the trans double bond already given. Another double bond we have here. So this is the product that we are going to get. If we get ethanol, so we are going to get this product. So this is very interesting examples. There are possibilities of coming this type of example because the examples with carbon-carbon decarbon system will already a lot of times appear, but this type of example did not appear. So if you are interested, then you can read this paper. See the fantastic paper, which is basically covers the carbon-carbon uh, fragmentation thing. So this is I am writing the reference. The review paper and we can review paper in educations, and this is the recently reviewed 2013 volume number 52, page number 233. So this is examples. Now, if I change the position of the OTS group, then what will happen? The logic behind general coverage is that couple of just 2 or 3 years back, it started the covering reactions from directly journal. It is happening. That's why I am showing some examples, related examples for journal. If the OTS group is here, then what will happen? So this is the OTS group. This is nitrogen. Now look, these are anti-peripheral conditions. Then what will happen? This is going to break. Sorry, this is going to delocalize, this is going to break, and this is going to leave. As a result, what we are getting? This ring will be remain intact, no change. There we have the double bond. There we have this double bonds. This is the hydrogen, as usual it was here, and this is the hydrogen here, and here is N double bond CH3. So when OTS is these positions, we have different products. If I combine these two examples, the previous examples, then in one film like that. I hope you are enjoying these examples because this example is very relative or related to the previous topic. Hydrogens on the OTS group is here. Upon hitting this molecule is going to produce these alkenes. Nitrogen plus double bond and one double bond is here. So the same molecules, same architecture, just OTS group changing the positions and double bond is changing. So this is example of gamma amino. See always it is in gamma positions. alpha, beta, gamma. So nitrogen will get gamma position. So this gamma amino fragmentation. It is the same reference paper. Next, another example. Not in this fashion. So let's see, this is the 5-member ring. Now I show the another possibilities where the fragmentation is possible. OMS, methyl group. If I treat these molecules with methyl magnesium bromide, very important or interesting example. So it will attack at carbonyl carbon. As a result, we'll have these things. This is CH3. This is O minus now. We have methyl group here. We have OMS group is here. Then what will happen? When it will come back, look, this is going to leave. As a result, this is very short intermediate. We are going to these things. Here we have now double bond. This is the double bond. We have one methyl group here. This is the methyl group. And here this is C double bond O and this is C. We are going to get these things. And upon, as we are using methyl magnesium bromide, then again it will attack there and we will have alcohol. So we are going to get again because this is again will attack there and we will get this is alcohol. Yes, is there. Wait. So just for your interest, so when you see in the next time I'll show you. So this is actually this type of fragmentation was, the famous scientist Esnosa. So this is the scheme that was used by this scientist. So this is the scheme taken from directly his paper, and also you will get this example in the same review article. Again, the recipient example because if something is given that is that the extended level of the fragmentations means it will not stop at fragmentations. It can go beyond fragmentation. That's why I'm including this example because so if you give that only it will stop at fragmentation, so you will stop it here. But as is a methyl the reactive group is here, then just it will be extended. That's why I put these examples. So another type of fragmentation reactions I'm showing you. See, the system is conformation locked. Here we have bromine atom, it's hydrogen. Hydrogen. It is a totally known chemistry. So if we try with zinc and just let's say solvent is GME, you know that zinc has a very much friendship with bromo. It will make a zinc bromo complex organ of zinc. So this is now lead and Br. This is Br, hydrogen, and this fragmentation will happen there. So look, these are anti-peripheral and this is going to leave. As a result, we'll have this alkyl. So this one breaks. So no change in this ring and this one breaks. Where here is one double bond in these positions and one double bond in this position. So this is the thing that we are going to get. So this is the fragmentation by another reagent. And again, we will get it in the same paper. So If you are interested, just download the paper. There are many examples. I have not taken all, but these are related. You should not read all the examples. The type I am going to show you is the actual five to six type of fragmentations. Your question will be within these types. It should not be outside this type. So this is another type of fragmentation reaction. Let's see that better. Epoxides. We have double bond O here. This is methyl and this is methyl. So if we treat this molecule with this hydrogen derivative, then what will happen? Acid phosphorylation will happen. Just it will be double bond N, NH and GS. And here with the epoxide methyl. Now treat this with the base. Then it will be N minus because the base will deprotonate. This question also came since CS and net. Directly this question is given. Then what will happen? After that, it will delocalize, will come here, and this epoxide will break. So the epoxide breaks now. This is now O minus. This is the methyl group. We have double bond here. So this is nitrogen. This is N. And this is GS. Then what will happen? This O minus will come back. This bond is going to break here, and this is going to leave, and this is going to leave. So we are getting a triple bond. This is the triple bond I tried first, and this is the methyl group here, because the triple bond here with this methyl group. The triple bond, this carbon contain on methyl group. That's why this is that methyl group, and now I draw the rest of the things. Double bond. This fragmentations, because it's an alpha beta epoxy ketone. It's an alpha beta epoxy ketone. So the fragmentation is called SN-Moser fragmentations. And the scientist who discovered these fragmentations, he gives the previous scheme directly. This is very noteworthy examples. So that is when the fragmentation will happen at the hydrogen derivative of alpha beta epoxy, we are going to get triple bond. Triple bond. That hydrogen of alpha beta epoxy derivative. Okay. This example directly came in CSNet. We'll see another category examples of this kind of things. Okay. I told it will fall in the category of these examples not given in the characters book. This is from the journal. This double bond O, and here let's think it is given some CO2 review. We are not bothering about that. Look, epoxy group at alpha beta position. So it is in the same framework. And what we are doing, we are doing the same reagent. TS, NH, NH2, and acetic acid required. We will not go into the details. The solvent. So this is falling in the category of this thing. So there will be a triple bond. Okay. So where will be the triple bond? It will be, if this is 1, 2, 1, 2, so it will be there. In this position, that triple bond will be there. So triple bond will be in these positions. Let me draw the, okay, maybe I am on carbon more or less. You do it in your notebook. What is the right one? Just I'm showing here will be the triple bond with respect to the after one carbon. This is the carbon here. This carbon is this one. After this carbon, the triple bond will be here. That's why next to here. So this is the clue how to get the position. So this is the carbon. So this is again another full of examples. And third example is generally used for real purposes. There are direct lines with examples. I will show you the chemistry behind that. Let's say this is the whole n maybe 0, 1, 2, and this is the R group. If we use nucleophile here, then what will happen? So nucleophile has a tendency towards this carbonyl positions. So what will it do? It will be O minus. We have this now nucleophile. Just I am showing the chemistry. I said I will not show you the product. This is R. So when this will come back, this will break. So again we are getting the alkyne, sorry, alkyne kind of things. If this let's say it is R, so we are getting now it is double bond O. We have this nucleophile, and this is the whole N system and R. So triple bond through fragmentations is created in case of the alpha beta unsaturated as well as beta epoxy carbonyl. Two types is possible. One is alpha beta unsaturated systems followed by nucleophilic attack, followed by NU attack, and second one is hydrogen derivative of alpha beta epoxy kind of things. Okay. Now another example pool is here. In the second category, double bond O alpha beta unsaturated R1, and here is OTF. Triplet is a good living group. This is 410. So just if we try with nucleophile, same examples. O minus nucleophile R1, OTF, and pollen. So again, we have this kind of systems. Double bond O, nucleophile, or N, triple bond. See another examples of different type. Let's say, by remembering, we have OH group here, we have H group H, and this is H2, and oxygen is here. Then what will happen? We use TSCl. This is another type of fragmentation reactions. This is now OH group will be converted into H. Now this is OTS, and this is OH. Look, we have used, you can ask why this is only one is going to be converted. See, this is more sterically congested, and we have used one equivalent of TSCl. That's why it will remain free and it will be tosylated. So this is the reason. So it is 3-degree alcohol, this is a 2-degree alcohol. So that's why it is OTS, this is even weight. And pyridine. If you use pyridine, then after that a base was used. In this case, especially just instead of writing base, whatever the base they used, I'm writing these things. So that you did not become puzzled that this is the base they used. So base will deprotonate this bond will break, this will go there, as a result, this will leave. So again, we are going to get fragmented product. So just again, I maybe 1 carbon more or less. You do on your way. Yeah, this is the double bond. So this is another type. So mostly all our things may come with this type. Another type is also there, but that is very much complex. I don't think this can come in CSN. So if some question comes from fragmentations, believe me, almost there is a 99% possibilities all this type will be coming in between these shown things, because this is the totally the coverage of Carothers, Helian Sanva, Cherry March, Playgen, and this important journal that contain this fragmentation reaction. Next, so I'm going into another different reaction. This is called Bamford-Stevens reaction. It is also interesting. So this questions came at GATE 2010 from this. Directly the question was asked. Bamford-Stevens reaction. This is not fragmentations, but this is a very small reaction. Just I will show you. So if we have a hydrogen derivative, as we are discussing about hydrogen, that's why I include this example. Let's say it is R double bond N NH. This is SO2 AR. So this is the hydrogen derivative. If you treat with this a strong base methoxide, then what will happen? The methoxide will deprotonated this NH proton. Double bond N minus SO2 R. So this will be minus. And this lone pair, one step, just I have didn't show here. If you heat this, then what will happen? We'll have these things. R double bond, and here a lot of interesting chemistry is hidden, but this is not for real chemistry learning. This kind of session, so just I'm skipping that part. If we heat this again, strong heating, so this will produce a carbon. So nitrogen will leave, and we are going to have a carbon here after strong heating. This carbon can go into a lot of side reactions. But one reaction is that CH abstraction. Once this CH abstraction happens, we will have alkene. CH abstraction. So with this alkene, hydrogen. So you can ask that why not the CH abstraction from this R group? Because it produces the more substituted alkene. Substituted alkene produce. That's why CH abstraction from this carbon. Okay, so this example directly came in GATE. So it is very much applicable for the cyclic system. So think about the system. It's maybe given with carbonyl, then one reaction can be given with a tosyl derivative. Let's say it is tosylated, or it will be directly given to this kind of things. Another 5-member ring. Yeah, and something is there. I am not drawing that. It is also they are not drawing that. So it is given, and after that NOM is there, strong base. I am solving this without any mechanism. Then what will happen? These positions will have double bond, just these positions. So we have these things. Double bond, and this is as usual. We are not going to that thing. So this is the tricks, and something is TS is like that. Tosyl group is double bond O, double bond O. This is benzene ring, and this is methyl. So this is the example of Bamford-Stevens reactions. And this is a conformation lock position. This is conformation lock positions. Two envelope kind of ring is fused together. So there should not be any double bond here. That's why the double bond will be these positions. So this is also another valuable reactions.